Okay, so for the second part, I'm going to start with I'm going to start actually with something that I forgot to say. I just saw that I forgot to say. I forgot to say what theta SP is. Theta SP is the spread. So here, for example, if you have a book to market variable, if you create, for example, the HML portfolio, what you have is a book to market spread. So the book to market spread is going to be proportional to the risk of the firm. If the book market spread increases or decreases, the risk of the firm increases or decreases. So this is one of the reasons, for example, why the HML portfolio is riskier than the S&P portfolio, because the book to market spread takes the 70th and 30th percentiles, the difference between these, and the size portfolio just takes the median as the breakpoint. But that's basically what I meant. So the risk of the portfolio is going to be proportional to the spread in whatever characteristic you use, could be book to market or size, and then this function here that tells you how the characteristic relates to risk. But anyway, nothing changes. It's still the same implications. The implication here and the implication for causation theories is the same. So nothing from what I said changes. It's just to clarify what this is. Okay, so now we can talk about the intertemporal explanation. So what happens here is first is what I think that it's an obvious but ignored fact about portfolio formation is that, and here is the main point of the paper is that if you look at price and you look at book to market and you look at the effect that the price of risk has on the correlation between price and risk, then it's immediately clear to see that the correlation cannot be constant over time, right? Because what you have here when you look at this equation, you basically have that the slope of the regression or the line here that links prices with risk is going to be given by the price of risk. It's actually if you have a very small price of risk, it doesn't need, I will talk about this later. It's not exactly this. It's even, let's say, worse than this. But basically what you have is that if you are in a state when the price of risk is very low and you rank by size, you're not going to capture any difference in risk. You're just going to capture differences in expected cash flows. Because if the price, imagine that it's really zero. It cannot be zero, but I say it's very close to zero. Then basically what you have is that price is equal to expected cash flows, and that's it, right? So when you split this into small and big, then you're just taking a bunch of risky and safe stocks in the small portfolio, a bunch of risky and safe stocks in the big portfolio. There's no difference in risk between these two portfolios. There's no premium, and then of course the size premium is going to be zero, right? And that's exactly what I find in that other paper, that one from that I said about the 10% of the years. Now, why is this important? Well, because as soon as you go to a high price risk state, if you're in a very high price risk state, now differences in risk they start to matter, right? So if two stocks that have different risks and the price of risk is very large, then these two stocks are going to have. It's very likely that the riskiest stock is going to have a lower price. If you want an example, a concrete example, just think about the banks during the financial crisis. How many banks were actually small caps during the financial crisis? It's not that banks were always riskier; they just became riskier because of the financial crisis. So during the financial crisis, they became very small, and and that's exactly this type of effect that I'm talking about here. If the price of risk, and it doesn't need to be, here I'm talking about the price of risk, like the norm of the price of risk. I'm talking about one-dimensional risk. That's not a vector there, right? So I'm talking about one-dimensional risk. I'm talking about the norm of the fact that's the Sharpe ratio of the mean variance frontier. But it's actually true for each individual risk. So if a given individual risk uh, is has a very high price, this is going to have an impact on the price. And then basically what you have is this: you have that if you create the portfolio, if you rank the portfolio, and that's what I mean by the fact that it's ignored about the portfolio formation. If you rank the portfolio, if you form the portfolio in a low price of risk state, then there's no correlation between risk and size. There's no risk in the size portfolio. If you do this in a very high price of risk state, there's a lot of risk in the portfolio because you split the risk and the safe stocks very well in these states. Now, if you compare these with the book to market, and here is where the dark matter starts, not exactly here, but like on the dark matter affects the how this is related to this. It's actually the relationship between these two. This is true anyway, right? As long as book equity is a good proxy for expected cash flows for some stocks, this is going to be true because in low price of risk states, where you basically have nothing to like, it's so noisy that you cannot say that you ranked anything by size. Let's say it cannot be zero, of course, because if it's zero, then all of them are zero. Like both of them are going to be flat. But if it's a little bit above zero, this one can still be flat, and this one is going to be positive because this one controls for the difference in expected cash flows of at least some firms or all of them. It doesn't matter, right? So here my dark matter assumption doesn't matter as long as book equity is a proxy for expected cash, is somehow correlated with expected cash flows. You're going to get this. So what do you get then? You get that the size premium in low price of risk states is going to be smaller than the value premium in low price of risk states. And I'm going to show that this is exactly what we see in the data. So this part doesn't need the black matter. This one is the one that needs. And how do you go from here to here according to the assumption that I made? Well, the assumption that I made is that that book equity is a good proxy for expected cash flows, but just for a small number of firms. So what happens is that this helps if you don't have anything to lose, and you don't have anything to lose here when you are in a low price of risk state because this one already doesn't work, right? So you can put as much noise as you want in the rest of the firms as long as you control for the cash flows of some of them. You're going to end up with a more efficient portfolio to capture risk, and that's exactly what you get here. That's what is represented here. Now, when you go to the high price of risk state, and that's the problem, based on the assumption that I made, what you're doing is you're inserting a lot of noise in the ranking by dividing by something that's not the correct measure of cash flow. So the first 10% you're still doing great. The first 5% you're still doing great. So there's no chance, no change between here and here. The other firms are still getting better aligned because they're becoming cheaper, so it's okay. But you are inserting some risk, some randomization in the ranking by dividing by the wrong price of risk, by the wrong book equity. Like for example, you are dividing the expected cash flows of Facebook by the book equity of Facebook, which is very low, and then you end up thinking that the stock is overvalued, for example. So this is the assumption that I'm making, that somehow when the price of risk is high and the sign that you get from the price is already very good, you are losing part of it because you're adding noise to the ranking. So what is it that I'm going to find as um, uh, a rejectable hypothesis, or what's the observable aspect of this? Well, the observable aspect of this is that the size premium is going to be larger than the value premium in these states. So the size premium is smaller in low price of states, is larger than in high price of states. This is what I'm getting. And this point here, which is important in the paper because that's actually the only formal rejection that I have of the causation theories. It comes from this. Unfortunately, I could not do it in another way. It comes from an assumption that is essentially unmeasurable. Um, right. But I also provide some evidence supporting the assumption. But that's basically the most important point of the paper. It's to understand that the state in which you form the portfolio is going to change the risk of the portfolio. This has implications, for example, in the Fama and French factor, right? Because it means that the factors that you form every June don't have the same risk. They have completely different risks. Like in one state they have no risk, in the other state they have high risk. The book to market also, they have one risk in one state, another risk in another state. If we want to do this a bit more formally, and that's what I have here for one-dimensional shocks, still for one-dimensional shocks, let's just look at how the correlation between risk and price changes. It's going to change with, well, here you have the variance of the expected cash flows. Those are all cross-sectional variances. So that's the variance in cross-sectional cash flows. And what you have is that this is going to increase as the price of risk increases. That's lambda t. As the price of risk increases, this is going to approach 1. So that doesn't have any assumption apart from the present value identity. For book to market and risk, then I have that assumption, and I have also an extra assumption that the variance of expected cash flows is equal to the variance of book equity. The reason for having this is because then I get this simplification here that it's going to be exactly the same as here, but it's going to be 2 times the variance of expected cash flows or book equity, and then 1 minus the correlation between them. And here is where that story, the dark matter, enters, because now this is going to be equal to 1 for when the correlation is strong. That's this S here is for strong. When the correlation is strong, it's equal to 1. There are 5% of them. When it's 1, this just cancels to 1, which means that the correlation starts at 5% and then it increases at this rate here, at the rate that this thing here increases. And then you can see that, well, here you have just variance of expected cash flows. Here you have 2 times the variance of expected cash flows, almost multiplied by 1, because this is very small, right? So it's much like this number here is much larger than this. And for this reason, this correlation is going to increase faster than this. So this one is going to be more sensitive to changes in the price of risk than this one, which is essentially what I have here, right? In this type of in this representation here, right? What is the other thing that I was telling you about the Fama and French type of portfolios? And it's not only the Fama and French; it's every all of these multi-factor models that use size or price related portfolios like Zhang and Su. I like the other the 4-factor models. There's the Stumble and another one also. So all these other factors, all these other multi-factor models, they are just for something that is related to size. And what the result that I just showed you is that the assumption that there is some risk intrinsically or constantly correlated with size cannot be true, right? Because if you now look, like here I had a one-dimensional risk and I just cared about one-dimensional. But now let's see what's the correlation between a particular risk. So this is the element S in that big vector of risks. So it's just like sigma S is the exposure of the shock, the exposure of the stock to the shock S, to the particular shock S. So what's the correlation between the exposure to this particular shock, just one element in the vector, and price? Well, it's going to be equal to all these numbers here, but basically what matters is that it is proportional to this is the risk premium that more or less the risk premium that you get from the cross-sectional variance in risk premium that you get. Actually, if you put this inside, it's going to be the risk premium. So it's the cross-sectional variance in risk premiums that you have, that this shock generates, and this is the cross-sectional variance in all the remaining risk premiums. So what this means is that the risk that is going to be more correlated with price is going to be the one that generates the highest cross-sectional variance in risk premiums. Now, what's the problem of this for the idea that there is a risk intrinsically correlated to size? Well, the problem is that the risks that generate the largest cross-sectional conditional correlation, the largest cross-sectional risk premium is not the same the risk is not the same in every period. For example, exposure to mortgage was a very important risk during the financial crisis, but it was not important before the financial crisis. Now we have exposure to coronavirus. It's a very important risk during the coronavirus, but it was not important before. So this type of risks, they only manifest, they only become correlated with price when they have a very large cross-sectional, when there is a lot of differentiation or a lot of spread in the risk premiums associated with that. and this is the point of this is why the Fama and French portfolio cannot adjust for any risk, because the risks they keep changing. Every period they're going to change. Like if they form the portfolio today, it's going to capture coronavirus. If they formed it in, um, in the financial crisis, it was capturing mortgage, and if each time it's going to capture one risk. And that's the point that I make here. It's not always the same risk. It's not the same as risk, not exposure to shocks that arise from coronavirus exposure. It's sometimes coronavirus, sometimes mortgage, sometimes anything. So it cannot be. And that's just the present value identity. I didn't make any dark matter assumption or anything. It's really just the present value identity. It already implies that it cannot be true, that the risks are always the same. Now, the same thing happens for book to market, right? And although I keep the dark matter thing, it's not because of the dark matter, right? It's actually just the same explanation. So it's unnecessary to keep this thing. It's just that for the same reason that price is not related to the same risks, then book to market cannot be. One important thing is that all the risks that are captured by book to market, it must be because it's captured by the price. So if the price doesn't capture always the same risk, then book to market cannot capture the same risks either. Right. So what type of parameters they fit the evidence? And this is going to be important to. It's kind of like the extended dark matter in the paper is to say, well, let's see what type of parameter can generate the type of result that I want to explain in the data. So, for example, if I use the variance in expected cash flow is exactly equal to the variance in book equity, that's an assumption, and that's part of the dark matter in the paper. It's going to be equal to 3.2. Why 3.2? Because this is if you take the fifth percentile, the breakpoints, the market equity breakpoints in Fama and French, in Kenneth French website, take the log, take the variance, you'll find that this is the average variance each month. I mean, take the average of the variances each month, you're going to find 3.2. Okay, so that's the 3.2. Then you have a standard deviation that I'm assuming that it's 15% per year. So it gives, this is the variance in the risk. So it's the variance of risk of this of sigma I in cross section. So it's 15%. That's going to give you the 0.225. And then the same thing that I already said before about the relation between book equity and cash flows. This is the main one, right? These ones we can change. I will show how to change how the results change afterwards. But this one is the main one because this one is the one that generates, and that's the main reason for that. This one is the one that generates this type of pattern that we see in the data. That the value is riskier than size until a certain point, until 2 in this case, and then size becomes riskier than value. Now this is about the correlation, and we cannot observe this because this is we are measuring the correlation with risk, which is unmeasurable. I mean, we are describing the correlation with risk, which is unmeasurable. We can get the same thing here if we change, for example, the correlation that I said that was 1 was if the correlation is until 9, then we get something between 2 and this value, and then we start to see that there is some differences. Like if it's here, for example, if it's exactly 0.9, then size is always riskier than value, and that's a problem for that's why the dark matter actually matters. If you change when it's the weak part, then it doesn't give like that. If you change the proportion of firms that are very highly correlated with expected cash for each book equity and expected cash flows are very highly correlated, and here the variance of expected cash flows. It reduces, right? So if you reduce the variance, you reduce the price of risk that's necessary to change one from one to the other. Right, so what we get from as rejectable implications then? Let's to finalize this. Well, the main rejectable implication that you get, the first two main rejectable implications that you get is that size is going to be larger than value. now we're talking about the size premium, right? So now I'm applying all these numbers. I'm applying all these numbers here, and I'm constructing the HML and the SMB portfolios. I'm also applying the fact that the HML here, that's why it moved from 2 to 4. I'm applying here the fact that the HML portfolio is a bit riskier than the size portfolio because it's based on 30, 70 percentiles, and the SMB is just the median, right? So that's why it moves here. But basically, the important result is that you have higher value premium than size premium in low price risk states, higher size premium than value premium in high price risk states, right? So this is the spread test. And there's another one which says, well, another important one is that, and that is that below a certain level, there is a threshold here in which the size premium is going to be starts to be significant in sample. So if you go increasing the if you increase the price of risk enough, you're going to find that the size premium becomes significant. And below that value, below that threshold, the size premium is going to be insignificant. And that's a threshold that's important because this is the threshold that I'm going to use for the classification of what is a high and what's a low price of risk state. There's also another detail here, which is that this continuous line like this assumes that there is a continuum of firms. But that's not true, right? The firms are actually discrete. So the correct line is actually a kinked line like this, and then like this, and then like this, and then like this, because what you need a price of risk that's high enough for the first firm to go from the group of big firms, the first risky firm, to go from the group of big firms to the group of small firms. Because if you don't have this type of if you don't have a high enough, it's not just anything above zero. It must be high enough for the first firm to go from the group of risky firms to the group of safe firms to the group of risky firms. Basically, you need to swap one risky firm that is in the big group for one safe firm that is in the small group. You need to swap these two firms, and then you create an imbalancing risk between the size, the small and the big size portfolios. And so all of this is to say that it's not only a statistical point, it's also asymptotically there would be another one that's actually smaller than the one that I consider, um, that makes the size minimum zero, even asymptotically, if the price of risk is too small. And because these things depend on a lot of unobservable variables, then I don't really talk much about this in the paper. All right. So what is the correlation hypothesis then? The formal correlation hypothesis that depends more on dark matter is this: is that the spread, given that the price of risk is below a certain level, is going to be positive. So the spread is the spread between the value and the size premium. The size premium is going to be larger than the value premium. Sorry, the value premium is going to be larger than the size premium if the price of risk is low. That's what I have here. And the spread, which is the value premium minus the size premium, if the price of risk is large, is going to be negative. So that's the first one. And there's a similar result in spanning regressions, but only high price of risk states. So sorry, the risks are similar in spanning regressions, but only high price of risk states. So what we have here in this solution is that we know that according to this theory, value and size, they need to correlate with the same risks. In the low price of risk states, value is not related to any risk. So what's going to happen in low price of risk states? If you run a spanning regression, well, there's going to be no R squared because they don't relate to the same risk, so they don't have any reason to be exposed to the same shocks. The R squared is going to be very low. The book to market, the betas, because the R squared is low and because there's no correlation, the betas are going to be very low. The beta, the exposure of one portfolio to the other is going to be very low. So if you run the regression of HML on SMB or SMB on HML, the beta is going to be low anyway. And also not most important, but another result is that if you try to regress the value premium on the size premium in these states, then the HML portfolio, the risk of the HML or the premium of the HML is going to be mostly unexplained by the size premium, by the SMB portfolio. So what you get is a very large intercept in these states. This is what happens when the size portfolio is not correlated with risk. And for this, again, just to stress where it's needed and where it's not, this doesn't depend on this assumption about whether size is more, sorry, value is more correlated in one state than in other. That's not important. The only thing that's important is that the size premium, the, the market value of equity is uncorrelated with risk in low price of risk states. That's for low price of risk. What happens in high price of risk states? Well, now we have two portfolios that are exposed to the same risks. What needs to happen then? Well, first of all, one needs to, if you run a spanning regression, there must be a very strong factor structure among these portfolios. So the R squared needs to be very high. The betas also need to be very high. And that's one of the points that here for this one I actually need the dark matter. The HML, the intercept of the HML portfolio is going to be lower. The reason why it's going to be lower is because, okay, both of them are going to be higher in this state, but the structure is going to be such that, where is it? That the risks that correlate to size, they actually contain the risks that are correlated to value. So here is where the assumption, that dark matter assumption enters. It enters on the alpha, right? So all the other results are independent of that, but the alpha, for this alpha you need. And also it's important that these are not exactly formal tests of the theory, right? Because these, I cannot really reject one from the other. So it's not a formal test, it's just a further confirmation that the theory is right. This one is the formal test. All right. Yeah, let me have a break again.